This is the Sanford Underground Research Facility, the deepest underground lab in the United States. It's a converted mine where more than 10 experiments are being conducted. Experiments that can only take place far beneath the surface of the Earth. We will tour 3 different labs where scientists are studying dark matter, the nature of neutrinos, and geothermal energy. Finally, we'll look at the construction of one of the largest particle physics experiments in the world. This is Wired Field Trip. 4,850 feet below the surface, researchers make their way to their experiments every morning. On the deepest level, you might think that scientists are studying the Earth's core, but instead, these physicists need nearly a mile of rock to shield their experiments from the sun and space. First up, the Lux Zeppelin experiment, a dark matter detector known as LZ.
LZ is a dark matter experiment trying to directly detect the dark matter particles that we think are flying through the Earth all the time.
So, what exactly is dark matter?
We think we know, as a species, how much stuff there is in our universe, but it turns out that the stuff that we understand, the stuff that makes us up, me up, the things that you see around me, is only about 5% of that total. So 95% of the universe's content is a mystery to humanity.
Dark matter is often referred to as the invisible glue that holds everything together. Physicists and astronomers have been hunting it for decades, all the way up to Hugh. Here's how the dark matter detector works.
So there are many, many layers to LZ. You start at the center with a large bucket of liquid xenon. Xenon is the heart of our experiment. It's the target material. It's what we hope the dark matter is going to interact with.
This is a cross-section of the experiment. In the center is the element xenon in liquid form. The xenon is housed in a chamber that includes many layers. Not only various elements like titanium and gadolinium, but a huge water tank. And of course, 4,850 feet of rock.
So there are charged particles constantly hitting our atmosphere. Some come from our galaxy, some come from outside of our galaxy, some we don't know where they come from, but they're hitting our atmosphere and they make showers and showers of particles. Those things will light up our detector constantly. If you tried to turn LZ on the surface, it would light up like a Christmas tree and you wouldn't be able to see anything at all. In our depth, the rate of those rays is way knocked down so that we can actually run our experiment.
The detector also includes photomultiplier tubes to detect light signals that could show the presence of dark matter.
Effectively, what we hope will happen is that dark matter will hit a xenon nucleus, it'll create a little flash of light, a little flash of charge, and we'll collect those things to see the signal.
And all of that is housed in this whole facility. Hugh is going to walk us through what goes into maintaining the detector.
So behind me at the moment is part of our cryogenic system. To be liquid, xenon has to be held at 100 degrees below 0 Celsius or 165 Kelvin. So this steel dewar behind us is filled with liquid nitrogen, and it is connected to a couple of tubes that run down into the detector. So here we have the wall of the LZ water tank. It was built underground, as you can see, welded from these sections. So this is filled with something like 70 gallons of water. So if I open this, 70,000 gallons of water would rush out and drown us all. So in front of us here, we have what we call the xenon tower, which is another part of the cryogenics. If you see these sort of big boa flexible lines, there's nitrogen running through those lines to come down to the xenon tower where we have a few heat exchangers that cools liquid xenon. The detector itself has 10 tons of xenon.
That's about a quarter of the world's yearly xenon production.
One of the reasons we really like xenon for this experiment is that it is very dense as a liquid. It's something like 3 kilograms per liter. So that is denser than aluminum. So if you put an aluminum block in our detector, it would float.
Inside the detector is one of the most radio-quiet places on Earth. They've reduced the amount of radiation down to almost nothing. And there's so much more that goes into it.
So these are our electronics racks. Here's our spare parts, the SRV, a neutron generator, heaters, cryocooler. So in this room, we have our xenon compressors. So there's xenon flowing through these gas lines, constantly being pumped to purify the detector.
The majority of this experiment is the researchers collecting data and waiting and waiting and waiting for something to happen. So what happens if they discover dark matter?
So dark matter right now is probably one of the biggest, if not the biggest, mysteries in particle physics. So it would be a huge, huge deal if we discovered it. And it would explain this huge chunk of our universe that is missing and would open up a whole new avenue of research. But there is a chance that the dark matter properties are so weak or so different from what we're looking for that we will never see it. And it's quite possible that when we sort of end our dark matter detection program, we will never have found the actual particle. So that's a scary proposition, but it's true.
Before LZ, there was a smaller detector. After LZ, there could be a bigger detector. The more they continue hunting, the more they can rule out what dark matter is or isn't. Nearly a mile underground, possibly the most concentration of xenon in the universe. They continue to wait until a small signal changes our understanding of where we came from. This is only the first experiment we're looking at today. Let's go check out another called the Majorana demonstrator. This is particle physicist Ralph Masajic.
So here we are, a mile underground, studying the nature of neutrinos. The Majorana demonstrator is looking for a concept known as neutrinoless double beta decay. Neutrinoless double beta decay is a very, very rare decay that can happen only in a handful of isotopes. If some of these particles vanish during the decay, it would give us a hint of how the universe could be created.
The theory that Ralph's team is working on is that neutrinos, the subatomic particle smaller than electrons, are their own antiparticle. In order to study this theory, the demonstrator is even more sensitive than the LZ dark matter detector. We have to enter a clean room. The principle is the same as the LZ shield layers, reduce background radiation. Even human bodies give off radiation. That's why the researchers are decked out in personal protective equipment, including our crew.
Here we are at the Majorana clean room, and we're going to look at the detector today and see how it's made.
In the LZ experiment, the element the physicists were hoping to see reactions in was xenon. In Majorana, it's the isotope germanium.
There's only a handful of isotopes which can do double beta decay. Germanium is one of them. We often compare finding double beta decay to listen to like a single conversation in a full stadium. Maybe you go to a Beyoncé concert and it's loud and you want to talk to your neighbor and he whispers. That's what you're trying to achieve. So every kind of radiation is a background, is a noise, which you constantly try to overcome. The Majorana experiment is shielded against natural radiation with several layers of material. Starts on the outside with roughly 12 inches of poly, then a very heavy lead shield. So you see like the size of a lead brick is roughly this times 4 times 8 inches, and there's a few thousands of them installed in the shield. And then to the core of the experiment, where we have our electroformed copper, which is the cleanest copper in the world, and which is grown underground here. And inside this shield, we have this what we call detector modules. So you see this copper vessel, and inside the vessel are our germanium detectors, where we try to look for double beta decay. A germanium detector is roughly the size of a hockey puck, and they are arranged here in an array of detectors. The signals go along this crossarm through all the shield to this readout electronics, which are located here behind the shield. This whole assembly weighs several tons. So what we do is we place everything on ball bearings down here and very slowly push it inside. It has to be done very slowly because there's a lot of fragile electronics and you don't want it to vibrate or to shake or to break.
In order to assemble the detector, the researchers have to work in these sealed boxes that also reduce background radiation.
So this is our glove box where we actually assemble the individual detector units, build bigger assembly of strings of detectors, and then also assemble the whole module. Inside the glove box, you see all the individual copper pieces. If you look at these pieces, they can be as small as very tiny nuts. But these copper pieces also all go all the way up to the several hundred pounds heavy shield plates which you saw before in the outer shield. So at the end you're actually going to wear 4 layers of gloves. The 2 gloves we're already wearing, the rubber gloves, and an innermost layer for cleanliness. And now you can imagine you have to pick up very tiny pieces like these ones. This is roughly the size of a germanium detector, and you have to assemble it. Simple tasks like just putting a nut on a bolt becomes complicated as soon as you have several layers of glove on.
What else is a part of this experiment?
Here you see the readout electronics of the germanium detectors. This is a hovercraft, this is the copper bar.
One of the more unique elements of the Majorana demonstrator is that researchers are growing copper.
It starts with this very pure copper nuggets, and they're put into a bath with acid, where through an electric field they're very slowly Only the copper drifts to these bigger mandrels.
When the copper is ready, the scientists move it into the machine room to make parts out of it.
Once they come off, they look like this. So you have these massive copper pieces, which are then get flattened out, and the copper pieces end up like this.
All of this chemistry, engineering, and physics goes into discovering the nature of neutrinos. So what happens if they find what they're looking for?
If we were able to show that neutrinos are their own antiparticles, it would show that the standard model as it exists is not complete. In each process, the same amount of if matter goes in, matter should come out. If this is suddenly not the case anymore, you open up a whole can of worms.
These physicists are searching for invisible particles that our entire understanding of science can't account for. Do you believe in magic at all?
No. I don't believe in magic in the sense of there's a magician who can make things disappear. But the way everything fits together, the way that particles drift in an electric field, the way a germanium detector works is its own little magic. Physics itself has its own magic. I'm lucky enough that I'm allowed to work in what I love, so I love it. It's gonna be a lifelong pursuit for me, I hope.
The researchers are entering the next phase of the Majorana demonstrator project, which will go on for another couple of years. Let's get out of the 4850 and go to another level.
Welcome to the 4100, where we're studying geothermal energy.
Hunter and Paul are part of one of the biggest geothermal research projects in the country.
Geothermal's been around for a long time, and people have learned over the last few hundred years that they could use the earth to both heat and cool their house. And they did this through technology called geothermal heat pumps. This research focuses on a different kind of geothermal energy, and that is called EGS, or Enhanced Geothermal Systems.
Basically, not every country can be like Iceland, where there's a high concentration of volcanoes. The next generation of geothermal research is exploring the technology of hydraulic fracturing.
So the idea for EGS is quite simple, actually. You drill two wells side by side, you create a fracture that connects these two wells, and then you can circulate water from the surface down the borehole through the fracture and produce steam or hot fluid out of the other borehole, and that is where the energy comes from. Now just imagine you set those boreholes up like a radiator and you put fractures one right after the other. Now you have something that could produce power for tens of millions of people.
EGS Collab is studying how the Earth interacts with fluids underground.
We drilled 9 boreholes, with 5 of them targeted for stimulation and production, basically.
The goal of stimulation holes is to stress test rocks to gather as much data as possible.
These are the 5 boreholes in which the straddle packers will be deployed in. Packers are used in hydraulic fracturing, both in experiments and also in industry. This is a packer element and this is a packer element. You can think of these as Kevlar balloons. And so what we do is we inflate these with water, they seal the borehole, and then if we're pumping water in, it comes out of this little hole and it fills up the volume in the borehole between these 2 balloons. That will generate a fracture, or it will open a fracture if the fracture already exists.
Today they are sending a camera down the borehole to understand it more.
So what we're pushing in here is called an optical televiewer, and what that is a camera at the end of the probe that's basically taking 360-degree pictures of the borehole. And what we're seeing on this screen right now is a live image of the televiewer. You're getting a picture of what the core left behind, the open borehole and the rock formation.
Let's walk down the cavern and take a look at the rock.
These are core that were extracted during the drilling of these boreholes. This is the Yates amphibolite, basically a very dense crystalline metamorphic rock. You're talking billion-year-old plus rock, so this is like the foundations of life on Earth and so forth. This is a neat piece. So here we're catching the Yates amphibolite here, but also a quartz vein on this side. So a pretty neat 360-degree view of an intersection with different types of rock.
What else is part of the experiment?
This is the microseismic and source seismic acquisition system. These are fiber enclosures.
This is our RO unit, chiller unit, triplex pump. This is the DAC box. There are the brains of the system. This is an alcove. That's also where our coffee maker is because we're super sophisticated.
EGS Collab's data aims to be a proving ground for geothermal energy around the country. Before we leave today, let's quickly go back to the 4,850 level and check out what's down this cavern. Down here in the darkness, engineers are building the single largest physics experiment in the world.
The Deep Underground Neutrino experiment is a massive series of detectors a mile underground here at the Sanford lab that's going to detect neutrinos that are generated at the Fermi lab in Batavia, Illinois. And so those neutrinos will pass directly through the Earth to here, and we'll be able to see how neutrinos oscillate over that distance. The detectors that we're building are going to hold 17,000 tons of liquid argon each. And to give you an idea of the scale of what that is, that's 63 feet across, 63 feet tall, and about 220 feet overall length per detector, and we've planned for 4 of these detectors. So you can picture the caverns that have to be built to house those large detectors. So when the neutrino reacts, it's going to create a flash of light, if you will, and by creating this drift inside of the argon, we can actually move that flash in a way that we can observe it. So overall construction of the LBNF and Dune project will take over 10 years. Building underground is like building a ship in the bottle. We have to disassemble everything into small enough pieces to take it down underground. And when we get underground, we have to reassemble it in these large caverns, which are like the bottle. Everything we do is going a mile down a shaft, and it's got to fit inside that shaft. There's no two ways around it. We're not going to build a larger shaft. So everything has to consider that as we're designing and building this facility.
Even though these mine shafts are around 90 years old, they are still state-of-the-art engineering.
The hoists at this facility are very unique. In fact, there's 4 of them in the world that are like this, and they're incredibly well designed. They're a cylindrical conical drum, and so that conical section allows it to automatically slow down without changing the motor speed at all. As you go to the smaller diameter, you're getting less distance per rotation, and that helps you with the torque that's necessary to lift the conveyances. Everything about this project is unprecedented. The size of the caverns that are being built, a mile underground, unprecedented. The size of the detectors, unprecedented. The size of the collaboration, not quite unprecedented, but there's only about 3 that have ever happened that are of this magnitude. The type of science we're doing, the type of science that this facility in general is doing, is really unprecedented. And it's the type of things that my grandkids will read about in textbooks and be able to say, my granddad worked on that. This is the experiment that the particle physics community is really focused on as their top priority.
There are so many other experiments going on at the Sanford Underground Lab that we don't have time for. On this level, biology experiments are looking at extremophiles. On this level, equipment testing for various industries and NASA. Now, we have to go above the surface. And that's our Wired field trip. See you next time.